Welcome to Lecture 14, where we'll be covering the principle of virtual work. And today we'll be covering the Euler Bernoulli beam theory. Now I'm in chapter 8 of my book. Previously, we covered chapter 7 from my book. And right now, we're going to go ahead and derive the beam theory equations for Euler Bernoulli beam theory. So, going a little bit back to understand what we're trying to do, we're using calculus of variations to derive structural theories. The most advanced theory to date, or the most general theory, is 3D theory. And in 3D theory, we use the principle of virtual work and we set the external virtual work equal to the internal virtual work. And using that, we demonstrated how the Euler Lagrange equations using the fundamental lemma of calculus variations happen to be the equations of equilibrium, which was a significant finding because this Euler Lagrange equation that we found was also derived using the integral form of Newton's law, summation of forces equal ma. On the surface of the body, we also demonstrated using the fundamental lemma of calculus of variations, we found the Cauchy's relationship. Remember, we developed that relationship using the tetrahedral element. And using that element, I was able to derive the very formula of Ti equals sigma ij and j. But I want to show you or remind you that we found this relationship simply by using the principle of virtual work. We also found that in surface V2, ui equals ui bar, and that is prescribed. You can't have both of these prescribed in the same location. It needs to be either one or the other at every single location. So I think that was very clear. That was very powerful. This finding was very powerful. And then we went into bar theory, axial bar theory, which is this is here, chapter 7 of my book. So that's the one we're talking about there. And that one we discussed in lecture 13. And to remind you what we did there, bar theory now is a simplification of 3D theory. 3D theory is much more advanced, but just imagine if I have an airplane or aircraft, or I have a rocket, or I have truss systems for a bridge. It does not make sense to model everything 3D because it will be computationally expensive. Instead, we know that these trusses or the struts in aircraft or rockets will take only axial or compression load. So as a consequence, we use axial bar theory to 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 derive the governing equations for this kind of theory. The assumptions that we made was a bar can only stretch or compress, and I gave the examples of trusses that are used in bridges, but also struts that could be used in rockets, cars, aircraft. And we took the displacement field that we came up with, and this displacement field is consistent with the assumptions that I made above. We calculate the strains at step 3, and because if I know the displacement field is consistent with these assumptions, I can calculate the strains, and I found that there's only one non-zero strain. And then the next step, I invoked the principle of virtual work, which says the internal virtual work equals the external virtual work. And then I went in and start to derive or start to specialize each of these terms very carefully. Um, and remember, these tractions that were applied were on the surface, and we then wrote Ti 2 pi r because of that. Um, and notice how del U1 is the only thing that survives in all this, and that I wrote the equation here one more time, and I wrote it to simplify, so it was simple for us to follow it. And then I called double integral sigma 1 dA n, which is the internal force reacting the external loads. Similarly to a 3D theory where the internal loads are described as the stress tensor, very similarly is the internal loads in a bar that actually happen to be axial forces. So now you know where the idea of axial forces came from when you did a free body diagram. You may remember that you did cuts and then you put an axial force. Well, it comes from this. And then we demonstrated that integration of parts will leads you to this equilibrium equation here. And then we went and derived the boundary conditions. And then finally, we were able to find everything in terms of deflection. And given the boundary conditions of the problem, you can then find the solution to this differential equation. Notice here how you have time domain here, and then you also have spatial domain. Here, just to make sure you understand, ui double dot, u1 double dot is equal to the partial of u respect to time. So that's what that is. Okay. So today what I'm going to cover is Euler Bernoulli beam theory, is using bridges, is using towers, is using aircraft. You can model the wing of an aircraft using wing theory. Beam theory. The airplane itself or the rocket itself can be represented as a beam because it's slender and it's long. That's why you can do that. And that's the advantage of using this approach. Order Bernoulli beam theory was derived with the primary assumptions. The assumptions were that under deformations, the cross section will remain perpendicular to the neutral axis, meaning if this beam bent, then the cross section will always be perpendicular to the neutral axis. The cross section is smaller, usually in this theory, than the length of the beam, typically a T over L of equal to 1 over 15. T is the thickness, L is the length. And here, Q could be the distributed force, W could be transverse deflections. I'm going to be using a different convention today, but that's okay. It doesn't matter. The important thing is that you understand what we're trying to do. Notice here how when I bend this beam, the cross-sectional area, and let me make a different color so you can see that, the cross-sectional area here stayed perpendicular after deformation to the neutral axis. This assumption is very valid for very long beams. Just a second. So we'll continue then. I apologize for that little break. Just want to make sure we got everything in place. What I want to show you here, all I want you to focus is on the first picture at the top. When a beam bends, you're going to have that neutral axis that's perpendicular to that cross section. So again, that's the main assumption in this theory. I'll be discussing this picture at the bottom later, but I just want to give you that perspective. Secondly, you may have learned from mechanics of material that this is the differential equation that you get for beam. And you may have learned that the moment is given by this, and that the deflections are either you have the beam in either side, you are specifying W, or you're specifying W prime. You could specify both also. In those conditions, you have a clamp condition. So you've seen this before from mechanics of materials. If you haven't, I invite you to maybe even look at my statics and mechanics of materials lecture that I have posted in YouTube. And I'll perhaps even put a link below. But what I want you to do is kind of revisit that for a second and see if you know where that came from. Now, what I want to do in this particular lecture is to demonstrate the derivation of that because it will be a lot of fun to go through those derivations. So let's do that because it is. So now I'm going to derive Euler Bernoulli beam theory. And I'm going to make several assumptions in this theory. So this is a beam. And I'll select the cross-sectional area as a rectangle. Sorry about that. And this way is x1, x2, and x3. And the corresponding deflections u1, u2, and u3. And the first step is to make the assumptions for this theory. We're going to say that the cross section does not stretch. We're going to neglect torsion, so no torsion is applied. And warping, which means that the cross-sectional area stays planar. C, we're going to assume that the cross-section remains perpendicular to the neutral axis during deformation. We're going to assume and then we're going to assume the cross section remains planar. Okay, so the next step is to really understand what are the displacements assumptions. So what are displacement assumptions? We start with U1, which is the axial direction of this beam or longitudinal direction. And we're going to say that's equal to U1, small u1, only a function of x1. And I'll explain physically what's going on, plus x3 beta theta plus x2 beta. And the next thing is x2 in the x2 direction out of plane of this page. We're going to assume there's no deflection. So this beam does not deflect out of page, only axially and in the x3 direction. So look, refer to this figure on the top right to figure that out. U3, we're going to assume that's equal to small u3 respect to x1. So with that said, let's now study what is going on with this beam. So I'll draw the beam on the form configuration. And this is x1. So sorry about that. And that's x3. And this point here will translate. Let me call this point P. This point will translate and rotate potentially. So it will say it translates and rotates. So this cross-sectional area here rotates, okay, to point P prime. And the beam has bent. The beam has bent. And that's our neutral axis, which stays perpendicular to the cross-sectional area. So that's if you have a stack of paper that's fairly thin and you bend it, you expect the cross-sectional area to stay perpendicular to the neutral axis. If you take a very thick encyclopedia and you bend that encyclopedia, or a phone book, which they're basically non-existent, but if you bend a phone book, that edge, that very edge is going to rotate quite significantly relative to the cross-sectional, to the neutral axis. So as a consequence, you can see that for very thin structures, they're very long. When you bend them, the cross-sectional area will stay somewhat perpendicular to the neutral axis. So that's a very good assumption that can be made. So we can see here then that when x3 is 0, and now here we're not assuming, we're going to assume that u1, that this right here is 0. We're going to assume that's 0 because we're assuming that any rotation about the axis x2 that there's no deflection u1. But we can see here that when x3 is 0, that the deflection u1 is equal to u1, and that deflection represents this distance here. That deflection right there. But if I look anywhere else through the thickness, if the beam bent, then you can see here that this moved to the left while this moved to the right, some amount. And so our goal is to be able to figure out what theta should be for that to be the case. Now, if I were to now substitute the fact that the shear strain is 0 in the 1-3 plane. So in other words, gamma 1-3 is 0, and we know that because the angle change in the 1-3 plane here is 0, it's state 90 degrees, no angle change. Then I can write it partial u1 respect to x3 plus partial u3 respect to x1, and that's 0. And you can see here that this is a one-dimensional theory because all these variables u1, u2, and u3 depend on x1 only. And here, what I get is derivative u1 respect to x3, which is, in essence, just theta. So this is theta plus, and then this derivative respect to x1 is just u3 respect to x1, and that's 0. So I'm able to find the value of theta from this equation. So therefore, u1 is really equal to small u1 x1 minus u, and I'm going to use prime now, prime, because it's easier to write it. And here prime is going to mean derivative relative to x1. And so again, I get this times x3. So that's u1. And so now I know that if I look, for example, let's look at u1 and let's look at x1. x2 is really doesn't matter. And let's look at x3 and assume the thickness here is h. So that's h half. Let's look at the top surface. Then I get u1 x1 minus u3 prime x1 h half. You can see here clearly that this point here moved to the left. So yeah, it translated, point P translated to this point, but this point Q and R, point R moved to the right relative to P prime, and Q moved to the left relative to P prime, and that's because of this right here. So it is working out, and it is an assumption. We're assuming that the deflection for beam varies linearly. The axial deflection varies linearly. U1 varies linearly with respect to the thickness direction. So that's an assumption. You can make a different assumption. You can assume it's quadratic, for example. But Euler Bernoulli beam theory, the assumption is that it was linear, which is fine. That's the assumption that was made. So now let's look at the step number 3 is to determine the non-zero strains. Again, those are the steps that we're following. So non-zero strains, we know that epsilon to 2 is partial of u2 respect to x2. That's 0 because u2 here is 0. That's why. We also have that epsilon 3 is 0 because partial of u3 respect to x3 is 0. And this is really representing the fact that the cross-sectional area does not stretch. So we found that. And we also know that gamma 130, because the cross-sectional area, the cross-section stays perpendicular to the neutral axis. We already showed that. So cross-sectional area remains perpendicular to the neutral axis. And then we have the fact that epsilon 2,3 is 1/2 partial u2 respect to x3 plus u3 partial respect to x2. And note how u2 is 0 and u3 does not depend on x2. So therefore, this is 0 and that's 0, so that's 0. And then we have the other shear strain you could have is epsilon 1, 2. So it's 1/2 partial of u1 respect to x2 plus partial u2 respect to x1. And note how u2 is 0. We knew that from the displacement assumptions. And u1 does not depend on x2 at all in this theory. So clearly, this is 0. And the only non-zero strain that I get then is epsilon 1, 1 is partial u1 respect to x1. And u1 was defined as small u1 x1 minus u3 prime x1 times x3. So that's really u1 prime minus u3 double prime times x3, where u1 and u3 depend on x1, and a partial, I apologize for that, a partial, a prime represents derivative respect to x1, and double prime corresponds to this, second derivative respect to x1. So now I have the non-zero strains, and my next step is to really look at what problem I'm trying to study first, because I haven't even defined that. So let's look at that first. So say I have a cross-sectional area that's a rectangle, and this is x1, and that's x3. And I want to study this problem. I want to look at attractions applied here this way. This traction I'm going to call it Q, and I'm going to apply a pressure load on the top surface alone, P, and I'm going to call this width. Let me give you some dimensions. So the width here is B. I'll call this height H. So the thickness of this beam is H. The modulus of this material is E. And so I've defined the problem now. I haven't given all the boundary conditions, but I want to leave it open so we can determine what those boundary conditions could be. So now that I have non-zero strains, I can now calculate, I can now use I can invoke the principle of virtual work, which states that the external virtual work is equal to the internal virtual work. And what the principle of virtual work tells us is that the internal virtual work equals external virtual work, then we're going to have the system in equilibrium for every kinematically admissible displacement field where we can vary the deflections. And so now I'm going to use the principle of virtual work, and the internal virtual work is the triple integral of sigma ij del epsilon ij dv, and that's equal to the triple integral of the body forces minus rho ai, I'm sorry about that, u I double dot the accelerations del ui dv, and then I could have traction forces applied. So plus double integral ti del ui ds, and now this is what I want to work out. Now I want you to notice how I have that the only non-zero strain here is epsilon 1, 1. So this simplifies to the triple integral of sigma 1, 1 del epsilon 1, 1 dv. And I'll continue working the left-hand side if you're okay with that, because the right-hand side we can work it later. In this particular problem, there's no body forces. And so I'll continue working the left-hand side. I'll work the right-hand side later. So the left-hand side is sigma 1, 1 del epsilon 1, 1 dv. This is equal to the triple integral of sigma 1, 1. And now I'll take the fact that epsilon 1, 1 is this. So del epsilon 1, 1 is del u1 prime minus x3 del u3 double prime. And so I'll go ahead and substitute that. So I have del u1 prime minus x3 del u3 double prime. and that's multiplied, dv. And so now I'm going to go ahead and I'm going to try to separate these things so they're more clear. So I have this integral triple, and I'm going to write this integral from 0 to L. So the beam goes from 0 to L for simplicity. It can go from x1 to x2. And so then I have double integral here of sigma 1, 1. And this right here, this dv is really dA dx1. Okay? So dA here is dx2 dx3. Totally fine so far. And I'm going to do a little trick. So you can see here how del u1 prime does not depend on dA at all, because u1 only depends on x1. It does not depend on x2 or x3. So therefore, I can take del u1 prime out of this dA integral and can just put it this way instead. Notice that u1 only depends on x2, while dA here is dx2 dx3. So that's why I was able to swap it that way. And then I have the minus double integral area. And again, del u3 here does not depend on dA. x3 does depend on dx2 dx3, so that has to stay inside. So I have sigma 1 1 x3 dA del u3 double prime x1. I was able to swap this outside because it does not depend on a cross-sectional area, dx1. And so now what I'm going to do, I'm going to call this the internal force N, right there. N, X, and I'll call X1. I'll call this right here the moment M, X1. And let me look at physically, again, this is all the left-hand side. I've only worked out the left-hand side. So let me just write this again. This is equal to 0 to L, N, X1, del U1 prime, X1, minus M, X1, del U3 double prime, X1, dx1. That's the left-hand side of the equation. And so let's try to understand what has transpired here, okay? So the first step is to look at these quantities that I've called N and M. That's the internal force, and that's the bending moment. And again, it came out naturally from principle of virtual work. I didn't have to force anything. It just came out to be very natural that way, okay? We haven't really forced anything here. So let's look at that cross-sectional area and understand better what N means. Okay, so if I have this, and then I have a sigma 1, 1. So sigma 1, 1 means it's acting on the one phase in the one direction. So it's acting like that, sigma 1, 1. And the one direction is that way, right? That's how we define the coordinate system. Okay, and the three direction goes upwards. So sigma 1, 1 is acting on the differential area dA. So clearly N has to be the reaction or the internal force that reacts to external forces, and this makes total sense. That is the internal force. And you can see these units of force. Furthermore, if I have sigma 1, 1 times x3, so that's this distance here. That's this distance from here to here. That distance is x3. So isn't that the moment due to the sigma 1, 1 force applied? So that's double integral of sigma 1, 1 x3 dA. Okay? So that's a physical definition. N is the axial force that causes stretching of the neutral axis. This is the bending moment that causes the beam to bend. Very good. So I can continue. I can continue with these derivations. So let me go to the next page here, which is blank. I've already worked out the left-hand side, just the left-hand side, not the right-hand side. The right-hand side, there's no body forces. We talked about that. And out of all the UIs, I only have two of them that survive because U2 is 0. And then we can look at this quantity here as well at each of the surfaces. So let's work out the external virtual work. I worked out the internal virtual work. This internal virtual work. This whole thing is internal virtual work. Now let's look at the external virtual work. So I have the triple integral over the volume, rho, u1 dot, double dot, del u1, plus rho, u3 double dot, del u3. Let's look at that term as well. And then I have the traction forces. If I look at the body of material, I only have traction forces applied on this surface here, this surface right here, where I'm applying Q. Okay, well, Q is acting downwards, which is in the negative of the x3 direction. So that's negative Q, and that's per unit area. So actually, let me write it out so you can see. At that particular surface, that surface alone is T, only T3 is applied downwards. Okay, del U3, and that is dx2, dx3, that dA. Okay, because that traction is applied in this surface, just this surface right here, which is dx2, dx3. That's the dA. Okay, so I'm basically calculating this for every surface. So in that surface, T3 is Q, is given to me, and it's negative Q because it's acting downwards instead of upwards in a negative direction. Big U3, small U3, so this del small U3, which depends only on X1. So in essence, this right here becomes minus QA because del U3 does not depend on dx2 and dx3, and Q also doesn't depend on that. So in fact, I just get del U3 at x1 equals L because that's where the load is applied, at that location. So that's a downward load applied. And then I have plus double integral. And now I'm going to shift my attention to the top surface where P is applied, that surface here. And so that force is applied downwards. So that's also T3, del U3. But now this is dx1, dx2. And notice how T3 is P in our situation, big U3 is small U3, depends on X1 alone. And so I can now integrate respect to dx2 alone because none of this stuff depends on x2. And so that integral is a width, which is b. So I get plus, or it's actually minus because it's applied downwards, which is opposite of the x3 direction. So I have minus integral 0 to L P, okay, B del U3 x1 dx1. Notice how I'll call this Q bar, so it's units of force, and I'll call this P bar, which is units of force. Basically, these units of force, Q bar, and P bar is units of force per unit length. So I've calculated the right-hand side to some extent. I definitely want to expand this. So this right here, big U3, small U3, big U3, small U3. So this is rho, small U3, double dot, del U3. Now this is a little bit more complex because this is rho of the time derivatives. and I have small u1 double dot x1, and also a function of time, but I'm not writing that to make it easier, minus x3, and now I have u3 prime there, x1. Okay, so that's that one times del u1 double dot x1 minus x3. I apologize, there's no double dot there. It's just simply that. So I'm just expanding this term right here. Del u3 prime x1. Okay, so I'm expanding everything in that integral is what I'm doing. And rho factors out, of course, and I don't have to worry about that rho. There's no body forces, so that's why they're not showing up in the external virtual work. I can multiply everything here, and so I'll get, so let me continue, external virtual work equals triple integral of the volume, rho u1 double dot x1, del u1 x1, plus x3 squared, u3 double dot prime x1, and then I have del u3 prime x1, and then I have minus x3 times del u1 x1, and then I'm going to factor the rho out so it's easier to handle. And then what else we have? We have del u1 x1, so that's this term right here. I also have u3 double dot prime x1 there when I multiply it. And then I have also another minus, so this is plus del u3 prime x1 times u1 double dot x1. Okay. Close that, close this, and this dv. And all of these multiply all this stuff together. So I know it looks very difficult and complex, but nothing much going on. Just multiplying everything together. So nothing to be worried about or fearful of. I want you to notice how this does not depend on dx2 and dx3, which I'm calling dA. So for that particular portion of the integral, I have the triple integral or the volume, rho, and basically I'm going to integrate that now. So I get rho A, because none of this stuff depends on dA, so that double integral of dA is area already. So 0 to L. And I have u1 double dot x1 del u1 x1. And then I have this here, x3 squared, which does depend on dA. And there is something very interesting, is that the double integral of x3 squared dA is really I, the moment of inertia. You've seen that back in school in mechanics of material. So then I really get plus rho I u3 double prime x1 del u3 prime x1. And more interestingly is that this term here will go to 0 because the integral of x3 dA, and I'll write it this way, is 0, because if I integrate this through the thickness, you will find that this is 0. So that term completely vanishes, and these three dots represents the stuff I have not written at the top here for these tractions. Okay, so I'll continue writing those. So that's, now I get minus p bar del u3 x1, and all this is dx1, and then I have minus q bar del u3 at x1 equals L. So I'm done now with external virtual work. I need to now equate this to the internal virtual work. Now, one thing I want you to notice, I had a negative sign here, which I completely dismissed when I was working it. So I do have to apply that negative sign. I'll basically propagate it here by putting a minus there, and there should be a minus there, and there should be a minus here. So I apologize for that. And there's no body forces in this particular example. And now I'll use the principal virtual work to set internal virtual work equals external virtual work. And when I do that, the left-hand side was written as integral 0 to L n x1. And I'm not going to write x1. You know that n varies as a function of axial station. So del u1 prime minus m del u3 double prime. You can see that here. That's what I wrote there. So I'm basically transferring everything here for us to continue the work. And I also have these other terms, minus rho A, U1 double dot, del U1, plus rho I, U3 double dot prime, del U3 prime. And I can continue all this. So I have minus P bar, del U3, and close the parenthesis dx1, minus Q bar, del U3 at x1 equals L, and this is equal to 0. So this is what we get for the principal virtual work for the beam so far that we've been looking at. Now, this negative sign should have propagated. And so I didn't fully propagate it here. So let me do that. This is minus. And so now everything is in business. The internal virtual work equals the external virtual work. So this should be plus because I brought everything to one side of the equation. So the internal virtual work, just a second. So the internal virtual work is this. I bring this stuff on the right-hand side to the left-hand side. So these become pluses. So I apologize. And this minus, so again, I have multiple mistakes. This minus was really intended for the inertial terms. So I'm going to ask you to kind of rederive what I've done to make sure I got it right, and put in the YouTube comment whether I made a mistake so that we can all get it right. So this should be negative signs. This is negative signs, so that's positive now. If I bring it to the other side of the equation, and then this is also positive if I bring it to the other side of the equation. So again, I apologize for this number of mistakes with the sign convention, but we should be in business now. So the next step now is step 4 was to invoke the principal virtual work. The step 5 then is to now integrate by parts. So now we're going to go ahead and integrate by parts and have this term, this term, this term. So 3 terms need to be integrated by parts, right? So let's go ahead and do that. I have And I'm going to go ahead and do that on the next page. So I have n w1 prime, m w3 double prime, and then I have this one right here, rho I u3 double dot prime del u3 prime. Just make sure we're looking at this term right here. So that's the one we're looking at. Let's integrate our parts and see what we get. So when I do that, I get m prime del u1, m prime, m double prime, del u3 prime, del u3, rho I u3 double prime, del u3. And so now I have plus, minus, plus, minus, plus, plus, minus. And that goes back into the integral. This term goes back into the integral. All these terms at the bottom go back into the integral. So let's do that. So I have the integral from 0 to L minus m prime del u1 plus m double prime del u3. And then I have the negative of rho I u3 double dot double prime. And here is del u3. And then I have more terms. You have the remaining terms I have not written, plus rho A u1 double dot del u1. So that's this term right here. And then I have remaining plus p bar del u3 dx1. And then I have a number of boundary terms which need to be written. So I have plus n del u1. Then I have plus m del u3 prime. Then I have minus like this. And then finally I have, and I can combine the term there because I have this cross term here. And so I have this. I want to notice how there is a minus sign here. And the minus sign needs to be propagated. So I should have done this so that this becomes minus. I apologize for that. And now this cross term becomes minus. This becomes plus. And I have m prime plus rho I u3 prime del u3. So I'm combining multiple terms here. And nothing else. And then now I have to have that one too. So I have q there. Q del u3, which can be combined here. I can just combine it there. Right? So that's plus q bar del u3. And for problems like this, we can now invoke the fundamental lemma, invoke the fundamental lemma of calculus of variations for any del u1 and any del v2, u3. I'll get two equations and let me write them out. So this term here and that term combine to get minus m prime plus rho A u1 double dot is 0. Okay, so that's the first equation that we get. The second equation is m double prime minus rho I u3 double dot double prime. So that's this term, and now I have that term, plus P bar equals 0. And this is true between 0 and L. And they have a number of boundary conditions that need to be written. And they're all based on these ones here. And they're going to depend on what kinds of boundary conditions I have. So I look at the endpoints. I have the natural boundary conditions and essential. And this is true at the endpoints x equals 0 and L, x1, sorry. So natural boundary conditions are either n is 0 or u1 is specified, m is 0 or u3 prime is specified, meaning the slope is specified, and have m prime plus rho I u3 prime plus q bar is 0, or we have that u3 is specified. And let's double that. Okay, so this is what we get. And so now, so these are the boundary conditions we get. And we have the governing equations, the boundary conditions, and all the variables depend on x1 and t alone, time domain. So that basically is what we get. And now, what if I want to write the equations? What if I want to write the equations so that what if I want to write the equations so we can then solve them, right? So the first step, step 6, is to relate N and M, which are the internal force quantities, to strains. And I already defined that N equals the double integral of sigma 1 dA. But sigma 1 is E epsilon 1 dA. But there is a double integral of E u1 prime minus x3 u3 double prime dx3. Okay, so that dA is dx3 dx2. And note how the integral of x3 with respect to dx3 is 0, because from that will give you x3 or squared divided by 2 from minus h half to h half, that's 0. So therefore you get here, you get that this is EA u1 prime. Just this term survives because u1 does not depend on dx3 and dx2. So a double integral over the cross-sectional area is EA. So that's what we get. For M, I'll have double integral of sigma 1 x3 dA, which is how we define bending moment. Double integral of E epsilon 1 x3 dA. And so that's double integral of E, and that's over the cross-sectional area A. And so now epsilon 1 is what? U1 double prime, or sorry, prime. And I'll multiply it out like that. And note how, I'll continue here. Note how E u1 prime x3 dx3 dx2, this is 0 because this does not depend on any of this stuff, and the integral of x3 with respect to dx3 is 0 because that's x3 squared divided by 2, and when it's evaluated from minus h half to h half, that gives you 0. So I'm left with minus double integral area, and notice how this s squared dA times E U3 double prime. Because this does not depend on the cross-sectional area, I'm able to take it out. But this is the moment of inertia, I. And this should be x3, sorry about that. So in effect, I get minus AI U3 double prime, which you have seen back in school. You've seen this before. So therefore, the governing equations that I get, final governing equations, sorry about this, are the following. I have to substitute what n is into this equation. And when I do that, I get EA minus EAU1 prime, okay, plus rho A U1 double prime equals 0. Now, if you compare, that's what we got before for the axial bar. I'll show you that in a second. This is what we got for the axial bar. Very similar answer, but I didn't have an axial force applied, so therefore there's no Q. So this is what we got. Sorry about that for backtracking. I wanted to show you that that's what we got. And now I have the next equation, which is this one here, right here. So that's minus, and the minus cancel out, so it's plus EI double prime, or U3 double prime, okay? And then I have plus, and I have that P bar that I had. And then I have this one here, minus rho I U3 double prime equals 0. So these are the governing equations for the beam. U1 is the axial displacement of the beam. U3 is a transverse displacement of the beam. So what is very important to realize is I made some assumptions on this theory, and these assumptions in this theory here, principal virtual work is trying to give me the best Euler Lagrange equations I can get based on those assumptions. But you're going to violate a number of physics, but I still get the best Euler Lagrange equations I can for the problem. And so now let's look at the boundary conditions I can have. So kinematic boundary conditions. The kinematic boundary conditions are you can have a rotor, but it's pinned. So as rotor condition. Sorry about that. And that means that I only have U3 is 0. Okay, I can have a clamp condition. That means that U1 is 0, U3 is 0, U3 prime is 0. I can have a rotor like this. Here, U3 prime is 0, no slope, U1 is 0. Or I can have a fully pinned condition. So a pinned condition looks like this. That means U1 is 0, U3 is 0. So that's a possible boundary condition you can have for Euler Bernoulli beam theory, and that came from the boundary conditions we had. If you recall, we have these boundary conditions here, and I'm trying to show you physically what they mean when they're combined. So the final thing is the equilibrium equations the equilibrium equations are inconsistent. So if you look at the equilibrium equations for Euler Bernoulli beam theory, you're going to have that sigma 1, 1, comma 1 plus sigma 1, 3, comma 3 is 0. But that sigma 1, 3, comma 3 is a minus of sigma 1, 1, comma 1. But this is the minus of E U1 double prime minus X3 U3 triple prime. And when I look at this, if you integrate this, you get a non-zero value. So this is not equal to 0. However, we had stated earlier that gamma 1, 3 is 0, but by Hooke's law, sigma 1, 3 equals G gamma 1, 3, which is 0. So there's inconsistency between what I get here when I integrate that to get a non-zero value to this, which says is 0. But that is inconsistent because of the assumptions that we have made. And so finally, what I want to do is to talk about energetically conjugate variables. So in 3D, 1D, axial bar, 1D, Euler Bernoulli, I get the following. The 3D, in 3D, sigma j is energetically conjugate to the strain epsilon ij. In 1D axial bar, I showed how N is the internal force quantity that resists external forces and is energetically conjugate to EA U1 prime. And in Euler Bernoulli beam theory, I showed you how N and M are energetically conjugate, and now M is bending moment to EA U1 prime and the minus of EI U3 double prime. And this is very useful because it tells you what are the important quantities that need to be considered. And here notice how M is equal to minus EI U3 double prime, which is consistent to mechanics of material. N is EA U1 prime. And if I now look at what you learned from school, mechanics of material, notice how we got this equation and the boundary conditions shown here. So yes, we got the same answer as what you've seen before. Have a great rest of your day, and then we'll cover Timoshenko next.